All right. So last time, as we talked, like this is, for example, this is my model, the model that we built. You need to check four things. You need to check number one, that you have the mass source defined, and then you will find something it's called mass source, and make sure that the mass source has all the dead loads including the on weight and the flooring, both of them. So how can I make sure that I have the flooring? So you can double click on any, right click on any slab and check the loads. You will have the load pattern dead load 0.15. That means that there's flooring inside the dead load. So this is one thing to check it. Also, you need to check assignments to find if a diaphragm is assigned. So yeah, there's a diaphragm D1 assigned to the slab. And I told you about the diaphragm because it condensed the degrees of freedom into single degree of freedom for each mass. So this is number two to check it. What else? You need to check the stiffness reduction factors, and I showed you how we can reduce them for each element. So basically, you go to define any section, like frame section, for example, and then you go to column and modify, and then you modify these parameters. The columns, we said we are gonna reduce them to 0.7. The shear walls 0.35, the beams 0.35, and the slabs 0.25, and this is in the presentation. So if you need a reference for the presentation, you will find everything here, like all the recording from the lecture, the notes that I have, everything that was written in the board is here. I believe it's in lateral load analysis PDF, and also the seismic design, you will find it also here. So both lectures, like everything that I had on the board over the last few lectures, you will find it here. Same thing with the presentation that has all the factors that you need. Also the recordings. So all the materials are on Canvas. Okay, so once your model is ready, you can define the earthquake. And I told you that you need first to define a responsive spectrum function. And we are going to use ESE 722. And you need to double check the parameters, like based on the soil and also the risk category. So you go to the USGS website and get these numbers and put them here. And once you are done, you save it. And once you define the responsive spectrum, you will go to the load pattern and define earthquake in X direction, and then modify it, and then make sure that the parameters are entered correctly based on our building type. And once we are done, so all this from previous lectures, so I can run the model. All right, so I have run the model and I got the results here. So let's see how we can, for example, get results. So if you want to get number one, or let's just start with maximum displacement, number one. For maximum displacement, ETAPS is very sophisticated in getting maximum displacement. Basically, you will go to display and you will find something that is called a story response plot. So this is something, and make sure in the report you always have the profile of the building everywhere, because that's a tall building project. So I need to see how's the building look like before anything, and all the results need to be on the profile of the building, like maximum displacement, interstory drift, everything need to have the building everywhere, so that I can see how's the building look like, how's the outrigger look like, how's the shear wall is connected with the outrigger. And I'm going to show you an example project from students from last year, so that you can have an idea how is the final project look like. But let's start with getting the maximum displacement. So basically, I will go to display story response. And once you click on the story response, it will open a new window and it's going to show you how is the building displacement look like. But make sure of a few things. Make sure that you have the right case to show the response from. So right now we are working with earthquake X. If you look at this one, you will find that the displacement is very, very small, like 2.5 multiplied by 10 to the power -3. That means that the building displacement is 2.5 millimeters. from the dead load. That makes sense. Yeah, because the dead loads usually make zero displacement. Okay. But the case that I'm interested in is the earthquake X. Okay, because this is the one that makes the maximum displacement. The seismic in X direction. Let's see how does the earthquake X look like. See, right now the building has a displacement 1.2 meter. That makes sense. I put seismic on the building, and then the building is moving 1.2 meter. 1.2 meter is a really big number. Can you imagine you are living in a building and earthquake is hitting, so it makes 1.2 meter, which means that system is not enough to resist the earthquake. And that's normal, because when we design buildings, sometimes we get to the point, okay, this building is not stiff enough, so I need to put more shear walls. I need to increase more cross sections. So we do some trials, okay? But if you got 1.2 meter, 2.2, because some of you have a spacing between columns 4 meter or 3 meter, so they will get more displacement, maybe 2. We will continue with that. If you want to adjust your system, maybe if you want to put more shear walls and you can make the results more reasonable, that's fine if you want to do that. Like, for example, you can like come here and you put like a shear wall here and a shear wall from this column to this column, and maybe on the other side here and here. So you can increase the shear walls to make your system more rigid so that the displacement can be much better. Like yesterday, for example, I did on the same building, but I did something. I increased the column size from 1 meter to 1.5 meter. And I increased the shear wall from 0.7 meter to 1 meter. Okay, let's see how this impacted the displacement. So let's go to display, same model, same everything. And I just save as and just to change it the cross sections. And it was very easy. If you want to do that, you can do that as well. I mean, like you can go, what I did, I went to define sections, frame sections, and I went to the column and I modified the column's dimension from 1 meter to 1.5 meter. And I rerun the model. It takes like 2 minutes to change it, 15 minutes to run the model, and I get the new results. Look what happened here. Let's change the case from dead load to earthquake X. Let's just keep X. All right, look at this. It was 1.2 meter. When I increased, it went down to around 0.7 less. Oh, okay. So it's less than 0.64 meter. Okay, because this is 640 multiplied to 10 to the power negative 3. And it's like half meter. So the reasonable for a tall building is the height over 500, usually from 400 to 600. So my building height 3 multiplied by 60. So it's around 180 meter over 500. If you want to go to the upper limit, you can put 600. Maybe let's put this 600. So 30 or 100, so around 0.3 meters. So it's a 30 centimeter. That's that level. So what I should do, I should add more shear walls, more things to make the system more stiff. But if you want to stick with the building that I give to you, that's fine. Okay. So this is the very thing. So in the final results, I need to see this profile. Okay. You don't have to make it big. You can make it small because you have lots of models. So for example, you will show for all the models how's the displacement look like. If you have 10, you will show 10 of these just adjacent to each other. Okay. So this is the maximum displacement. And this is an X direction. Can you see the blue? The blue is X. The red is Y because I'm only showing what's going on in X. So the blue is the only one that has value. The red is just staying there. If I'm applying earthquake in X and earthquake in Y at the same time, so you will find both of them are having values. Okay. All right, so let's get to the next thing, which is the interstory drift. So this is the maximum drift, the maximum story drifts. So I just like clicked here and changed the case. All right, look at this. This is the interstory drift. The interstory drift is the difference between the drift from this story to this story. Actually, in the standards like AC 722, they don't have limits on the maximum displacement of the buildings. They have limits on the interstory drift. Usually the limits for the displacement come from the wind, but usually this is the most important thing in the seismic, because if I'm looking on designing column, the differential displacement between this story and this story, that makes the moment. Like if my column is mid-translation, I don't have any problem. But if it's making like not uniform translation, like this point is here and this point is here, so it's hard to bend. So that's why what is the value is. But why this shit is look like this? Why it makes this and then another one like this, and then it comes back because the outrigger. Okay, if there's no outrigger, this shit is gonna be something like this. You will not have these drops because the outrigger is very, very stiff. It didn't make like differential displacement. The column is bending, but you have a very strong story, so it doesn't have that much interstory drift. So this very important to show in your project for all the simulations that you have. Okay, so this is the interstory drift. So right now, okay, let's check these. Drift and interstory drift. The third thing, the shear lag. The shear lag is gonna take some time from you. Let's see how we are gonna do it so fast. The shear lag is keep it changing with the stories. Like if you are want to find the shear lag at the bottom, will be different from here, will be different from here. So what I'm asking you, you don't have to do it for each story. Maybe one story, maybe two or three. So three is very good. Like if you want to do to get a section in your building at any story from 1 to 10, maybe at the base you start with, and maybe one in story number 30 and one in the story number 50. That's it. Okay. So let's see how we can do it. So shear lag is basically a reaction, the reaction in the columns, because this is like you have a column here and a column there and a column there, and this building having an earthquake and keep bending. So there is tension in this building and compression in the other buildings, okay, or the vice versa. So what we want to do is we want to know what is the compression in each columns. If this is a perfect tube or a perfect cross sections, all of them should have the same tension or the same compression, but this is not a perfect solid section. It's a tube section, a bunch of columns connected by a bunch of beams. So it is not perfectly going up together or going down together. Okay, so let's see how we can get it. All right, so what I'm gonna do, let's get back to our original model here. So you will go to, for example, I want to get it for story number 1. So I will go to plan story number 1. Okay. And let's start with this side. All right. I'm studying earthquake in X direction. All right. Studying earthquake in X direction. That means that the earthquake is hitting this building in X direction. How does the shear lag on this side should look like? Should it look like something like this? Or this shot, or this side should be something like this? I have the earthquake is hitting this way. So how's the shear lag on this side should be look like? This one or this one? Because we have the shear lag should be like something. If it's a perfect, so this should go down. If it's a perfect tube or a solid section, this is how the behavior should be look like. But because it is not a solid section, there is lagging in the shear, something like this. All right. So we have two shapes of the shear line. One of them is like the one that is changing linearly, like something like this, and one is on the other side. So if the earthquake is hitting from this side, so I'm supposed to see this one, the one that makes a curve like this, because this comes from if there's a load is coming this way. So if the load is coming this way, that means there is a bending moment this way, and this one side has tension and the other side has compression, right? Okay, so let's see how we can get the values. So what you will do is you will select the columns that you want to show the reactions on. So I'm gonna select all the columns on this side. All right. And then I'm gonna go to display show tables because I want to show a tabulated value for the reactions or the internal forces in these columns. So tables is very, very important and effective tool in ETABS that you can show the values on many elements at the same time. So I will go to show tables, and then I will go to analysis results, and you will find something is called joint output and element output. Since we are selecting columns, columns is not joints, it's an element. So I will go to element output, and then there's something is called frame output, and then you will find something is called columns. So I'll only select the columns and make sure that you want to show results for the selected only, because if you didn't check this, it will show the results for all the columns in your project. So I want to only show the selection. And make sure that you show the reactions in these columns for one specific load case. Like I will go to select load pattern, which earthquake X only, because that's what I'm interested in. And I select the load case to be earthquake X. So right now I'm gonna show the reaction in these columns if they got hit with an earthquake in X, and just for these columns, not the columns in these in the entire project. And then I will say okay. Once you say okay, gonna show you table like that, has a story because all the columns are in story one, the column name, but you will find the name is repeated many times, and you have all of them coming from earthquake X. But column C63 has three values. It says it calculates the internal forces at different stations of the column, like at 0, at 1, and at 2. So what I'm interested in, usually this makes like, this is important when you having moment, because the moment is a changing over the length of the column, but usually the compression doesn't change. So I'm interested in P, the force, the axial force on the column. So this one, okay? So what I'm gonna do, I'm gonna filter these columns and only show station number 0 at the base of the column. So you can right click here and filter and make this only equal to 0. And then I will say apply filter. So I'm gonna only see the reactions due to earthquake X at station number 0 only, okay? All right, so next is I'm gonna take this column, the one that has B to Excel, and I'm gonna put it here. And I'm gonna say this, for example, column number 1, column number 2, and you will tell me, okay, but this column name is not 1 or 2. I will tell you later why did I do this. But one thing that I need to double check here, I make sure that these columns numbers are in order. Like 63 is the column over there, and then 64, because if they are mixed, I need to arrange them. They are arranged, but there's only one thing that we need to make sure, because sometimes ETABS name the corners verse, and then they start to name the other columns. So let's check where's 63 and where's 64, column number 63 and 64. All right, so I will close this, and then I will show here, I will go to display. I will click on this check mark, which is set view options, object assignment, labels. I want to show the labels on the columns, and I will hit OK to make sure that they are named the same way. So I'm gonna make a close-up view here. All right, I'm not sure if you guys can see it or not. Here's 63, and this is 84. Okay, let's see where's 64. Okay, so I'm gonna zoom out and then zoom in down here. You will find, I'm not sure if you'll see this or not. It's a 64. So 64 is down there. So what I want to do is I just move 64 from up after 63 and move it down at the end. Okay. So so you'll find here after this, you will find that you have 65 and everything's right. So I'll come here, I will only move this down.
Should we move the first one?
Both of them are equal, so it will not matter that much. So, and then you will plot. Let's plot this, X and Y. So I will go to insert here and here. And this is how's the shear lag look like? Can you see? You'll tell me, okay, so why is it look like this? It went down and then it goes up again and then make like this. Why didn't go all the way down? Does any of you have any outriggers? Because of the outriggers. Because you have an outriggers in your model. So when you come at the middle of the building where you have a core and this core is connected with the outrigger, this is where the core is. It's connected with the outriggers. So it makes a shift a little bit because it makes the columns at this area, because if you remember, we have our building like this, and there's a core here. And this core connected these two columns very stiff together. So they have a little bit of a stiffness that can take more tension or more compression. So more loads are transferred to these columns. So the internal forces went up a little bit. Okay. But however, when we go up with more stories, this effect can be decreased. So let's get it for other stories. Like for example, let me go here and then go to plan, for example, number 48. And then I'm gonna escape so that I escape the selection from the other one. I'm gonna select these, display, show tables, and then I will say, okay. I will need to filter the stations, just the station number 0. And then I'm gonna copy these, Control C, and then I will go to the Excel file. I will put it Control C, Control V. Let me do another story. Like for example, let's go to story, escape story number 55, plan. And then let me select these, display, show tables. Okay. And let me filter. Let me copy these. Control C. All right. So let me plot all of these. Insert. Okay. Oh yeah, I forgot to change the all right, let me get these two here. So right now, as we go up, the shear lag is almost about 0. Because why? Because there's no much internal forces. But once we go down, and that's what we usually interested for in the lower story, like story number 1. Like if, for example, let me pick another story, like let me pick like story, for example, number 5. So you'll find that the shear lag effect is still, but not as much as a story number 1. So let me pick story number 5. Let me do this, display, show tables. Okay. Stations, filter. Control C. And let me put it here, insert. All right. Let me plot these. All right. Can you see? This, the blue one is coming. Okay, yeah, I forgot to do the same thing. Let me shift this down and move all these up. All right, so it's a little bit of a difference, like they are not identical. Okay, so this orange one is different from the one at the blue. So yeah, so once we go up, this shear lag effect is gonna be less until you go to the opposite story. So the shear lag effect is not. Okay, so I'm done with the shear lag on this side. So what I'm looking for, maybe you pick a story number one and you get the shear lag at this story and that's it. And you get it for all the 10 models that you have and plot them maybe on the same curve, or if you want to plot them at separate curves and put them together, that's fine. As you can see, just take a second. You select the columns, show the tables, get to the Excel, and then plot, copy, or screenshot of the chart and put it in your report. So let's get the other side, how it's look like. On the other side, so same thing. What I'm gonna do, I'm gonna just click on this side. And then, by the way, this side should be the same like this side, but one of them is tension and the other is compression. So it's just different sign. Okay, so I'm just pick two sides. And then I will go display, show tables. I'll say okay. And then I will, the stations, filter 0. And then I will take the load B, Control C. And let me put 1, 2. And let me, actually this one, the numbers are right. Okay, how did I know? Because the two values at first are not identical, but if you look at this value and this value are almost the same. One of them is negative, one of them is positive. So that makes sense because I have one side is tension, the other side is compression. So let's plot this and see how's the shear lag look like. Insert something like this. So this is how's the shear lag look like. And it's the same thing. You'll find that there's something going on here also because of the outrigger that you have. Okay. All right, so that's what I'm looking for to see. Okay, so I want to see these curves for all the models that you have. This is very, very important phenomena when we deal with full buildings. There's other structure like boxed bridges. They have the same phenomena and you can plot it in a different way. But this is very, very important to understand what is the shear lag is and how you can get it. This is how we can get it. But by the way, this is how does the shear lag look like? But if you want to know the value of the shear lag, you need to do something else. Like if somebody tell you, okay, you showed me how the shear lag in the building look like, but if I want to know how this is deviated from the original shape, or how's the original shape look like and how this one is deviated from it. So what we do in real life, you have your building like this. And just for your information, and this is the base. We will get the moment at the base. How can I get the moment at the base? You will go to etaps, very easy. You will come here and then the same thing that we did with display. So we'll go to display, show tables. I uncheck this. And you will go to something is called the structure output because we want to get output for the entire structure, not element. And you will go to base reactions and here base reactions. And then you will select the load case. You make sure it's earthquake, and then you say, okay. This is how the base reactions look like on the entire structure. This is the amount of base shear. That's the value that I told you, the most important value when we talk about earthquake. When I say earthquake, the first thing that comes in your mind, base shear and responsive spectrum, because this is how you are going to solve your model. What is the value of the base shear on the building that this earthquake generated? This value, 21 ton. And for example, sometimes in interviews, they ask you, okay, if I have a building, the effective weight of the building is 200,000 ton. What is the estimated value of the base shear in the building without any calculation? Usually it's a 10% of the building effective weight. So if you have 200,000 ton building, like the building that we have, then 10%, so it's a 20,000. So I can right now, like if we want to calculate it, we can do it. Like maybe this can be a good exercise. Like let's come here. I just change one thing, display, show tables, and it's not exactly 10%, it's around 10%, 8, 10, 12. And let me change the load cases and include, for example, the dead load, because the dead load is the effective weight. And let me say, okay. So right now I included two things. So I have the earthquake. This is the base shear. It's around 21,000, and the building is 280,000 tons. So divide these two numbers together if you have a calculator and tell me what is the number. It's around like maybe it's less than 10%, maybe 8%, or 9% around this number. So this is how's the value of the base shear look like. Okay. Okay, so this is the base shear. The amount of moment on this building, and we are talking about the moment, like if we are hitting a building with an earthquake in X direction, the moment is about Y or about X?
7.6.
7.6, right? So it's around 10%, okay? So I'm hitting an earthquake in X direction, so the moment is about Y. So this is the moment on the building. If you look at the moment about X, it's almost zero. So the moment about Y, it's around 290, actually it's 2.9 million ton meter, okay? So we'll take this moment. This is the moment. If you look at this as a cross section, you have this moment. How can I know the tension on this side and the compression of this side knowing this moment? You can, because you have this distance. So there's an equation that you can get. It's sigma is equal to m over I multiplied by y. If you want to know the contribution of each column, like the tension, if you want to know the stress in this column, you will take this moment, the moment that you have, over the inertia of the column, and then you multiply it by y, you will get the stress. If you multiply the stress by the area, you will get the tension on the column, so you will know actually how much tension in each one of these column is, okay? So, and then you can actually write the black curve. And once you have the black curve, if this one, the actual one, you subtract the maximum from this value, and this value is the delta, okay? So this is the value of the shear lag. All right, so we are done with the shear lag. Does any of you have any question on the shear lag? Okay, so we are done with this part. The fundamental period. So to get the fundamental period, this is very easy. So all what you have to do is that you will go to display, deformate shape, and in deformate shape, you will show case. Rather than showing case, you will show mode, and you will show mode 1. Mode 1 is the fundamental period, okay? And you will see something like this. This is mode number 1, this one. And it shows here mode shape number 1, and the period is 4.8 seconds. When you change something in your model, increasing the stiffness of the columns or increasing the stiffness of the shear walls, what happened to this? The fundamental period is going to go up or go down? Like if I increase the stiffness of the building, the period is going to go up or down? Go down, go less, because the building is start to be more stiff. So the time that takes the building, it gets very stiff. So it's a small, okay? So like if I check, for example, the stiffer model that I did here was more building, and I will show, actually I'm showing mode number 3 here. So let me change it to mode number 1. I'll say, okay. It's the columns, I increased it. So you will find that the mode shape is 3.66. So the period goes down. And that's what I want to know, what happened to your model when you increase the beam size, when you increase, for example, the shear wall. So you'll have many things that you are changing. I want to know how this is affecting the fundamental period. Also, you can get it from different things. You can go to display, show tables. And from show tables, you will go to structures output, model information, and there's something is called model participating mass ratio. And then you will hit OK. It will show you the period from each mode shape. So it will tell you mode shape number 1 is 3.66 seconds, mode shape number 2 is 3.5 seconds. As soon as you get to the higher modes, the variance of each node gets less because to shape these nodes, you need much more force to generate these node shapes. Okay, but if there's a small, like let's assume that you have a small and earthquake is hitting the building. So the building is going to make a little bit of a displacement. So mostly the domination is coming from node one. But if there is a much bigger force, it's going to shape much more mass, and the higher modes is going to show up. But what we are interested in right now is the fundamental variance. So that's what I want to see. So what I want to see like a curve like this. Number one is model number one, model number 2, 3, 4, 5. Each of you have already like around 10 models, and you show how T is changing with each model. For example, something like this, right? Okay, so we are done with the fundamental variance. Base shear, I just show you how to get the base shear. You'll go to display, structure outputs, and get the base shear. So everything I showed to you, one of these, okay? So let me show you how I want the results in the final report look like. I uploaded yesterday in the course, something is called Final Project Report Template. You just need to click on this template and download it. It's a Word file. And what you are gonna do, we are gonna have the results in the form of a paper. Like this is an ASCE paper format. So what I want you to do, you put the name of your project and then the group names, and then you will write an abstract about what you are doing. So what we are doing is lateral load analysis for a tall building, 60-story. We are checking for the maximum story displacement, drift, shear lag, and then you write a two conclusion, because the abstract is telling me what you are doing and what is your result. Okay, just a summary, maybe 150 words here. And then the introduction, I want you to do a little bit of research. Did you guys remember the presentation that I presented about the lateral load resisting system? You will write a little bit about lateral load resisting system and what we are going to do, what lateral load resisting system that we are going to use, and all this stuff in the introduction. Okay, so a little bit of research to show that you have a little bit of a background about the lateral load resisting system. Okay, so once you're done with the introduction, the methodology. So for the methodology, we are studying the lateral performance of the building. And this is how we model the building. You need to show me that you use the ETABS and you show me the profile of the building. And this profile and with also the plan of the building, I need to see everything and what you are changing, because I want to know what is the parameters that you are changing, the coupling beam parameters, if you have bracing, if you have everything, you need to list everything in the methodology that you have. And finally, you show me the results. All these things, the maximum displacement, the drift, all the plots, it should be in the results. And finally, you make a summary. You tell me what is the best system that performs in your model, like which one is the best that you can choose, okay? And if you have any comments, like you will say, okay, I know that, for example, the total displacement of my building is 2 meters, and I know that this is high enough. We can do this to decrease it. We can increase the shear wall thickness. We can add more shear walls to tell me some recommendations how you can decrease this displacement, okay? What we are doing is not a real project. We are just like doing a practical, something that we can understand how's the lateral performance of the building look like. Let me show you a project from last year. Yeah, and also this is the final submission, the one that I will be waiting for you. You will have to name your model with unique names, like you name your model with something that is changing. For example, the coupling beam parameters, you put it here, and you say that I use a spandrel beam 50 by 60, and I use the coupling beam 30 by 90, okay? Something like this, and then you will put a Word file for the report, and I would recommend to put a PDF as well, and the presentation. We will have a presentation by the end of the semester, so all this should be the submission folder. And let's see how a good project should look like. So this is a submission from students from last year. They have the abstract. They talked about everything, about what kind of modelings that they are using. They have some keywords like a real scientific paper. And then they have an introduction about the lateral load resisting systems. And then they will have the methodology. And then they list what models that they are using, what parameters, because what we are doing is parametric studies. So you'll need to make it clear what parameters that you are changing. And here they are naming the models. We have this model and this model and this model, and this is the parameter that is a change. Okay. Then going down, they show the profile of the building. They have some tables. They showed how they used the US GS. So they showed me the 3D, the profile, the plan, everything. And then they show with outrigger, with bracing. This is how the bracing look like. And this is how the results for each model, the maximum displacement. And I would love to have a table as well that shows the value of the displacement up here for each one of them, and one plot like this for each model. And then what does the maximum displacement look like? Delta. And then you show me something, for example, like this, or a curve like that. That will be perfect. Okay. And the same thing with the interstory drift. How's the interstory drift look like? And the shear lag, as you can see, they put a shear lag for each model at 3 different stories. So they have around 4 by 3, 12 model, and they showed for 3 different stories. And they plotted how this is impacting the fundamental period and the maximum story this drift and everything, and then the conclusion, and that's it. All right. So is that any difficult? All right, so let me tell you, this is a step-by-step how it should be. First, as I told you, you'll have to watch the YouTube video, 1 hour, follow step-by-step, you will be able to build a model. So the model geometry is ready. Another video, you'll see how to enter the seismic load. It's just one box. You need to fill some parameters. And once you are done and you remember the 4 things that we need to make sure before we run the model, decrease the model stiffness, put the diaphragms, what else? The mass source, and there's one like from the last lecture, and I have it also in the notes. Okay, you need to make sure that these 4 things are good, and then and the mesh size, increase the mesh size to be like 3 by 3 or something, and then you run the model. Then you use the recording from this lectures to get the results and write the report. Okay, so it's really basic if you concentrate and know what you are doing. So it will be very, very simple. It will not be that difficult at all. Okay, all right. So any of you have any questions? Does any of you have any? Yeah.
Lab, we just do it for like when we're choosing like the columns, we want the 2 sides only.
It's better to have for 2 sides. Like it's better to have it this one and this one. If you want just do one side, that's fine. I just want to know if you were able to show me shear lag or not. Yeah.
Follow-up question.
Yeah.
All the results, we're just showing it for what, like the EQX, or do we do also Y?
We can only do earthquake X. We don't have to do earthquake Y. But in real life, when we design, we do earthquake X, earthquake Y, and we do load combinations. We put earthquake in X and 0.3 in Y, earthquake in Y and 0.3 in X. But this is not what we are looking for. Just doing analysis, not design. So earthquake X is fine. Right, and also our project is kind of symmetric. So what you are getting from X's will be kind of how it will be looked from Y. Do you have any questions? Other questions?
Okay, I think I have
Yeah.
one more. So for the shear lag, will we display the base one? It's not the one that's like actual base one.
Yeah.
With those numbers, we want to look at the graph.
Yeah, the graph that I just drew, like this one, like this one. This, these graphs. Here's that. Yeah, these ones, these graphs.
You said that was the actual value that's just like the unit.
Oh yeah, if you did this, that will be perfect. Like, okay, if you guys, okay, let me tell you, if you guys showed me how the the actual the building without shear lag, like if the building is performing like an actual solid section, on the top of the shear lag, and you calculated the maximum lag that you have, I'm gonna give you 5% bonus on your project. So if this is a case for if you're able to do it, I'm gonna give the group who did this 5% bonus. Like the grading will be from 105, not from 100. Okay, is that fair enough? If you don't want to do it, that's fine. Just from 100. Okay. Basically, this is the idea. You will get the moment, and then you will divide by I, and then you multiply by the y of how the column is far from here. Okay. For example, if the column here and y is equal to 0, so the stress here at this column is going to be 0. But once the column is far away from the neutral axis, it's going to have more tension. Let me do one thing to check. Yeah. Okay. So basically, the moment is going to be very, very big number. Like, for example, it's going to be 2 million, 2 to the 10 to the power 6 ton meter. But I is going to be very, very small number because the cross-section area, you guys know how to get the inertia, right? The inertia of the column, like if you have A and B, and we have earthquake is about this because we are looking, but they are like rectangles, so it doesn't matter. So basically it's A, it's B multiplied by A cube over, I believe, 12 or 4. 12, yeah. So it's 12, something like this. So you will know, you will get the inertia of this column, and then you will put it here. It's going to be a very, very small number. When you divide it on the big number, it's going to be much better. And then you multiply by y. So you will get the stresses, not the tension. The stress at this column, if you want to get the tension or the compression or B, you multiply sigma by the area of the column. Okay. And you do it. And basically, if you get this column, all these columns will be the same because they have the same I and the same Y. So you just do it for one column. Once the Y is changing, so you are doing it for all the columns on the line. So each one will have different tension until you get to the one in the middle. So it's going to have 0 because Y is equal to 0. Okay. So finally, we'll end up with something. This one has tension. This one has compression, and will be linear, something like this. If you plot the two graphs on top of each other, this is the one that doesn't have shear lag. This is the one that has lag. And you want to get me the value, because this is what I'm looking for, of the maximum lag. Okay, something like this. And then you will get delta for each model. And then finally, you plot delta with each model, 1, 2, 3, and then you will show me how does the shear lag look like. Okay. But let me make it much easier for you. You don't have to do it for all the columns on the side. Just do it for the last column and plot this linear line, like because all these columns is going to have one value. Like for example, if a moment is happening, if this moment this way, without lag, this one should be something like this, one value at this column. Okay, so you will substitute in this equation by only one value. The y of the last column at the end is going to be like this. And then you plot this on the same Excel file that has the shear lag. And you show me how it's look like. How I can do this, it's very easy. Like, let's say this is, let me insert a table, insert a column. And let's say without shear lag is going to be 3148. And it's going to be constant at all the columns because this doesn't have lag. Okay. So if I plot these, insert, plot this one. Okay. All right. Let me, if I want to make a line here, Okay, so this is the one that doesn't have shear lag. Insert another one. Okay, it doesn't. Why it doesn't show up?
And just add header for the first line.
Hmm?
And add title for the first line.
Okay, let's yeah, it's gonna be something like this. And if you want to get the maximum lag is happening here. And then you get a value for each one. So basically, this is how it's gonna look like. All right. This one that doesn't have any lag, and all the columns have the same tension, but this one, the columns are lagging in terms of the tension. Okay. And as I told you, this is represent the efficiency of the system. The one that has 100% efficiency is the one that has a solid line, because all the columns, let's for example say we have a line of columns, all of them 150 by 150, and when an earthquake hits, the one on the corners are taking most of the loads, and the one on the middles are not taking as much load as the one at the verse. So the one at the corners are working 100% efficiency, but the one in the middles they are not working 100%. So if we want to make it much more efficient, we need to decrease this shear lag as much as you can. Okay. So if you want to do this, you will get, but you will show me how you did this in details. How you calculate I, like you make a special section in the report and say calculating the shear lag value, and then you show me these two equations and how you substitute with the moment, the inertia, and y, and you get the value of b, and you show me values. You'll get the 5% points. Okay. All right, so that's it for now. We are done with the project. Starting next week, we are gonna back to the same thing that we used to do from the start of the semester. We're going to have around 8 lectures talking about how we solve indeterminate structures using different methods. And we are going to have midterm by the end of the semester. Okay. All right. So I hope during the weekend, don't waste time, because as I told you, we will have lots of things to do. You will have more homeworks. They have lots of homework over the last few, maybe the last week, but you were supposed to be working on the project. So what I recommend, so that you can keep up with the project and what's going on, is that you start in the weekends to get these results and work on the report. And don't wait, okay, I'm gonna run the models and I'm gonna write the reports at the end of the semester. So when you get a result, throw them in the report and describe them so that you don't forget what you did. Okay, so this is my recommendations, and see you guys next time. And if you have any questions while working on the project, you can email me. We can have a Zoom meeting. So if you're stuck with anything, right? See you guys next week.